So my name is Brian Nolan. I'm a professor in the School of Mathematical Sciences, and I'm the chair of the master's degree in Astrophysics and Relativity. So in this short presentation, I'll take you through a few details of that program. Okay, so here's a quick rundown on what I'll talk about over the next 15 minutes or so. I'll give you just an overview of the program as a whole, why we're presenting this program now. I'll talk about the structure and content of the program requirements, entry requirements, the career opportunities that come from this program, and then research opportunities that are associated with it. So first, a quick overview. Well, I would say that, of course, I'm involved in this area, but I think it is objectively a particularly exciting time in the areas of astrophysics and relativity. Over the last 6 years, there's been 2 Nobel Prizes in Physics awarded in this area. First in 2017 for the detection of gravitational waves by the LIGO Consortium, and then in 2020 a shared Nobel Prize among a few people, including Roger Penrose and Andrea Ghez, for various aspects of black hole physics. So there was the imaging of the black hole in the M87 galaxy and then subsequently in our own galaxy. And the prize was also awarded to Roger Penrose for his earlier discoveries about black holes. So it is a very exciting time in these areas. There's lots of new discoveries being made now, old problems being solved, new areas being opened up, new telescopes coming online, for example, the ILOFAR telescope, the Athena and the Cherenkov telescopic array, all of which DCU researchers have been involved with. So researchers in the Centre for Astrophysics and Relativity here in DCU have come together to offer this new MSc programme on these very exciting areas of physics. And at the same time, while giving you the opportunity to study, to explore the exciting science, equipping you with excellent employability skills. The structure of the program, well, the program can be done on either a 1-year full-time basis or a 2-year part-time. It's a 90 credit program, so 90 ECTS credits. The 1-year program is a full year, 12-month program. In the first semester, you cover 30 credits of taught material, attending lectures, tutorials, labs, completing assignments, mini projects, and doing exams at the end of that semester before Christmas. Similar in semester 2, running from January to April. 30 credits altogether, a number of different modules, and we'll talk about details of those in a few moments. So attending your lectures, tutorials, completing assignments, attending labs, and completing the exams at the end of that period. So, well, I can't really call it a third semester, but during the summer period, from May to August, you'll work individually on your project under the supervision of one of the researchers from the Centre of Astrophysics and Relativity. So that's assigned 30 credits, giving an indication of the importance of the project for the master's degree as a whole. In terms of the content, well, the program is built around these 3 pillars. Well, it's called a master's degree in astrophysics and relativity, and so, of course, those are 2 important components of the program. So the third pillar then is computation and data analysis. So we have those 3 pillars: general relativity, astrophysics, and computation and data analysis. In terms of the modules, how the modules in the program align with those pillars, under the heading of general relativity, there's one module in the first semester, and that's called differential geometry and general relativity. So differential geometry is the branch of mathematics that's needed to understand general relativity. This is the mathematics that Albert Einstein used to devise this theory. So we study that for the first few weeks of the semester and then go on to apply the physical principles identified by Einstein and see how the mathematics and the physics come together to give us this geometrical theory of the gravitational field. In the second semester then, you'll study 2 modules in advanced general relativity, one on black holes and one on gravitational waves. So under black holes, you'll study both classical and quantum aspects of black holes, looking at their formation, their black hole collisions, and quantum ideas around black holes. In particular, the idea of Hawking radiation, discovered by Stephen Hawking in this amazing insight of his that showed us that black holes are not really black when quantum processes are taken into consideration. In the module of gravitational waves, you will study the formation, propagation, and detection of gravitational waves. And again, this is a really exciting area, as the last 5 to 8 years, have seen the opening up of a fundamentally new branch of astronomy, a new branch of science, gravitational wave astronomy, that provides us with an entirely new window on the universe, allowing us to detect and understand events across the universe that are fundamentally undetectable in other ways. On the astrophysics pillar, you start off with a foundational module in semester 1 entitled Theoretical Astrophysics. So this is looking at the fundamental physics and some mathematics as well that's required to do the more advanced modules, and indeed to investigate certain processes in and of their own right. So you'll study areas such as plasma physics and aspects of thermal physics that are absolutely essential for studying such concepts as the formation of stars, their life cycles and evolution, how galaxies are formed. In the second semester, we have 2 modules then on advanced astrophysics, and as you can see, they're extragalactic astrophysics, studying galaxies, their interactions in the space between them, and high energy astrophysics, studying the most highly energetic phenomena in the entire universe, such objects as gamma ray bursts and X-ray bursts, collisions of neutron stars, and so forth. So again, you're blending the fundamental physics there, so high energy physics, and applying that to these extrasolar and to astrophysical processes and phenomena. The third leg of the program is goes under the heading of computation and data analysis. And across the 2 semesters, as you see, there's 3 modules there. 2 that you will study in the first semester on partial differential equations in the first hand. And this is a branch of mathematics that, like differential geometry, is absolutely essential for analysing and understanding the range of physical phenomena that you'll study across the program. So that mathematics module is accompanied by a module on computing covering data science and machine learning. So in that module, you will learn essential data analysis skills and some AI skills, in particular machine learning, that you'll be able to apply to a wide range of different scenarios. And in particular, there will be, through some of the assessment work, a focus on data sets that arise in the astrophysics setting. We have these vast data sets that need these advanced cutting-edge techniques in data analysis in order to understand and interpret the data collected by various telescopes. In semester 2, there's a module called computational physics, which does what it says on the tin. That's the application of advanced computational techniques to solving problems in physics. Again, something that's extremely important in astrophysics. Some of the mathematical equations are simply not amenable to paper and pencil study, to theoretical study, and require the execution by computer programs in order to predict the nature of solutions. And you'll be learning about that in semester 2, and developing lots of useful skills that can be transferred to a wide variety of different areas. So, for example, some of the computational skills that you will learn there are exactly those skills that are required in weather forecasting and in financial simulations and so forth. The program requirements are fundamentally a 2-1, a minimum of second-class honours grade 1 award in an appropriate degree program. So that degree program is likely to be physics or astrophysics, theoretical physics, mathematical physics, other branches of the mathematical sciences, maybe applied mathematics, or a closely related field, for example, engineering. The key thing for one of these programs in a closely related field is that you have the appropriate background in mathematics and physics. So not every engineering program would cover sufficient of those topics. Certainly a good few engineering programs will, and you'll be able to find the details on the program web pages on the DCU website as to precisely what areas of mathematics and physics are needed for the program. Careers, well, this program, this master's degree, is an excellent way to begin a career in research in those areas of astrophysics and relativity. So you'll have excellent preparation in terms of knowledge and skills, but also at the same time in terms of career progression, career development. Having a master's degree under your belt would put you in an excellent position for applying for a scholarship, perhaps through the Irish Research Council, the Irish government scholarship system, or a variety of other international and national scholarship schemes. So having a master's degree enhances your CV and gives you the first taste, I suppose, through the project of research skills, and perhaps will with a very good project, you may even have a couple of publications under your belt, which again will enhance your prospects of successfully applying for a scholarship. So this is an excellent pathway into a career in research in these areas, either here in DCU, elsewhere in Ireland, or indeed around the world. Likewise, now I've mentioned this third leg of the program, the computation and data analysis leg of the program, and that leg in particular equips you with transferable skills in computing and data analysis that have application in a huge number of different areas. So data science is being applied in almost every career these days. In particular, in IT and communications, data analytics, business analytics apply to business consultancy. Data analysis, data science is being applied in engineering and banking and finance in, as I say, almost all areas of economic activity. Data science skills are extremely highly valued at the moment, and you will develop those skills in the course of this program. So the project forms a third of the program, as we've seen. This is done over the summer. From May to the end of August, and it's done on an individual basis. So you'll be working on your own project, supervised individually by one of the CFAR researchers. This gives you immediately the possibility to work with a supervisor on a PhD funding application. This can be done during your master's degree or following its completion. In terms of areas of study for those projects, well, it's between general relativity and astrophysics. So just to mention a few of the topics, a few of the broader areas under which you could study your project. It could be in black hole physics, it could be in studying gravitational waves, looking at the problem of motion, for example, the motion of two black holes as they're orbiting around one another, ultimately colliding and emitting a huge burst of gravitational waves. You may choose to study quantum fields in curved space-time, or quantum gravity. Again, all of these areas being areas in which there's active research work in CFAR. Or you may be interested in working on some of the mathematical problems, some of the deep mathematical problems that are thrown up by the physical situations described by general relativity. Under astrophysics, again, a wide variety of topics are available for study in your project, maybe relating to astrophysical plasmas, black hole formation in the early universe, protoplanetary disks, or high-energy astrophysics. So that incorporates these exotic objects such as gamma-ray and X-ray sources. And colleagues here in CFAR are also active in the scientific preparation for the Athena and CTA telescopes, and projects can be done that relate to that work. Okay, so that's all I wanted to say about the program. I'm very, very happy indeed to take any questions that you may have about the program. There's my contact details, brian.nolan@dcu.ie. Just watch out for the spelling of my first name there, Brian with an E. Further information about the program you can get directly from the DCU website.